hope my audio I'm audible. And just to remind you guys that when I'm presenting, that time my screen the whole screen is covered with the presentation. So in case if anyone of you has doubt, so please unmute yourself and say it out, okay? Because I won't be able to see your raised hands. Okay. With that, let's come to the presentation. Okay, so good afternoon, everyone. Very welcome to this second interaction session for Solid State Physics NPTEL course. You all know the course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, a PMRF research scholar from School of Physics, University of Hyderabad. And if anybody is joining for the first time, these sessions we'll have along with these weekly lectures that will be uploaded. So at the end, like on every Saturday, we'll have these sessions where you guys can ask your doubt on, because these are live sessions. Otherwise, I'll be recording all these sessions and uploading on YouTube as well. Link also you'll have access to. But if you have some doubt and you want to ask one-on-one, please be present in these sessions. There we'll be discussing or revising few topics already taught in that week's lecture. Also, we'll be doing some related numerical problems so that it will help you solve your weekly assignments and at the end the exam. Okay, so again, these sessions are held on every Saturday, 3 p.m. to 5 p.m. Indian Standard Time. Okay. So, the recommended books, last time also I had said, sorry again, this is for a second. There are 4 books that are recommended, and you must have seen they are mentioned on the website itself. And I would recommend, this is a good book by Charles Kettle, and later when we will be studying about X-ray, medicality, this is a very good book. Okay. So last session we had started first understanding about what this course is about, as the name is solid state physics. So which part of nature we see, solid, matter, different kind of states the material exists in, and why solid state is important and what we want to study. We had started from very basic, if you remember, by after understanding what are the different kinds of matter that are existing in nature. After that, we moved on to understanding atoms, and that we also discussed quantum numbers. But more important than that, we discussed how stable matter exists. Means we were discussing the force between two atoms and how they finally exist at particular distance from each other. Any two atoms. This is the center, the neutron. The neutron and positron is at the nucleus, right? So, and then electron revolves around the closed shells. So how the atoms end up being at particular distance and then make up the whole matter, be it any element or material or compound. That we had seen that there is electron repulsion between them, which will which will make repulsion between the two atoms, and the positive core will also lead to repulsion. Like, just to revise, electron will lead to repulsion, interaction will lead to repulsion. The positive core of the two atoms will lead to repulsion as well, whereas the electron of this one atom and the positive core or this nucleus of another atom, they will lead to attraction, because this is positive charge, this is negative charge. Similarly, the nucleus of this atom and the electron on another atom, they will lead to attraction. So we have two things which are leading to repulsion between the atoms and two things which are leading to attraction between the atom. Then eventually, where will they stay? Where these repulsion and attractive forces will balance each other out? That we had seen happens like this, that when two atoms are at very far away distance, there is attraction between them, and when they are too close, there is repulsion, strong repulsion between them, and this is energy and this is the distance between the atoms. and the energy is minimum, that is the atoms will be stable at the distance r0. Here the repulsion and attractive forces will balance out or cancel out each other, and at this r0 the atoms will be stable. And we had discussed how nature or any system in universe prefers to be at equilibrium or in stable state, because it leads to minimum energy. Okay, so this we had discussed. Then we had discussed about different type of bonding that is there between these atoms, covalent bond, primary and secondary. Broadly we had discussed that, and then underneath primary and secondary we had discussed the subcategories. After that we had moved on to understanding, we had moved on to understanding that solids are made up of different atoms, but how the arrangement happens. So before going on to understanding lattice, we had also discussed that we have something called crystalline solids and amorphous solids. Right? Amorphous, like something like glass, and crystalline, something like some element, atom, or NaCl crystal or something like this. Why? Because they have order in them. The atoms are following some particular order. In amorphous, there is no order. Like, they are randomly arranged. And why this ordering and presence and absence of ordering matters? Because it leads to change in properties as well. So when they are ordered, they behave in certain way. When they are disordered, their behavior is completely different. Okay, so this ordering, if you see, they are all like same pattern, right? We were talking about. So this we had understood crystalline, and under this also we were talking about single crystal. This we see when throughout that object, throughout that material, the pattern is same from the beginning to the ending. If this is some material, then from the beginning to the ending the pattern is same, then it's single crystal, that is single ordered, single pattern is being followed. Whereas polycrystal, we call the material is said to be polycrystalline material when this order is very short, like for I'll draw here, like up to certain distance it's following one particular pattern, the atoms in that material, and after a certain time it's following some other pattern after some length. So if you will see only this small portion, you will see it's ordered. Another this region, when we'll see it's ordered, but overall not single order or single pattern is being followed from like all over the material. So that's why we say that there are different ordering, like different number of ordering. So this is called polycrystalline, this is called single crystalline, and when there is no ordering at all, it's called amorphous. So after this we had understood that something known as lattice, these terms, lattice, basis, and crystal structure. That lattice is a mathematical concept. We were seeing, right? Like we were talking about the ordering of these atoms. So this is how it was understood by scientists, that we have some ordering or pattern of mathematical points. So it doesn't exist, but just mathematically we say that there is ordering of these points in space, be it 2D space or 3D space. Just in space there is some mathematical or regular ordering of these points, and when we keep basis on these points, then we get our crystal. This, right, we were saying single crystal, polycrystal. This crystal we get when we keep basis on these lattice points. And basis, what we had understood, it could be one atom, so it could be one this basis could be one atom or a group of atoms. This also we had seen example that either I'm keeping one atom everywhere, so I'll get a single crystal like this, or if I have in my basis I have one big atom and a small atom, and I'm repeating this and putting it everywhere. Like this is my lattice arrangement. Again, it's just abstract. And when I keep this group of atom, which is my basis here, again you will see there is an pattern being followed. Although now I have two different type of atoms, but still we can clearly see that there is a pattern, because the big ones are at particular distance from each other, the small ones are from particular distance from each other. Also the big and smaller are at particular angle and distance from each other. So still we can see some regular arrangement. So bases can be single atom or a group of atoms. There could be more than two atoms as well. But the pattern should be there. Okay. So this, when we put bases at lattice point, we get a crystal. Now we'll further understand how many types of crystals are there in nature, and and further we'll try to understand their properties. Okay, also to mention why we are so curious about understanding such a small portion, because what we see around is the objects that we are able to see from our naked eyes, right? Like a metal box or a brick or something. Then why we are interested to go at that atomic level and understand? Because it's something like, if we understand a small portion of a material, it will help us understand the whole material or predict its properties. Many times that goes very correct. It's like doing a survey that we see. So it's not possible to reach out to every person on earth and get to know information from them. So usually what's done is we take some a number of people, we try to keep as homogeneous as possible, but some people, and we do a survey and we find out the information and we think it's true for the whole country or the whole city, something like that. So similarly, when I have some material in solid form, if I'm able to understand its crystal structure, I can predict with crystal structure, I can see its arrangement of atoms. Then I can say, I can think about, I can predict its physical properties or chemical properties. And then, so I don't, I mean, it's not always needed to do some measurement for whole thing or in some other ways, but this is why we want to understand it from the basic building block of that material. Okay, anyways, so moving on. So we understood lattice, basis, and crystal structure. Yeah, this was the example we had seen last time also. This is lattice arrangement. It could be any angle to each other, only there should be a pattern. Please keep in mind there should be a pattern. And then associate an atom, we'll get a crystal structure. And here we have a basis of two atoms. When we'll associate with every lattice point, we'll get another kind of crystal structure. Okay. Till this we had understood last time. Now we'll move on to understanding this crystal structure. And yeah, okay. So this crystal structure is something like this, right? Like this we see. This is in 2D right now. Just X and Y we have. And this picture, as you can see, it's 3D, because 3D gets a little difficult to visualize on this screen. So I have taken help of this picture. If we talk about 2D again, so let me just these are my atom arrangement. And I'm not drawing the lattice arrangement here. We have just directly taken the crystal. But of course, there is lattice arrangement and associated are these bases, and then I am getting this crystal structure, right? Just now we discussed the same thing. So I have this crystal, and now here we see that these four atoms, if I repeat it, then I'll get this crystal. This whole crystal of, let's say, 5 by 5 atoms it contains, right? Yeah. So the whole can be, or whatever, 6. I mean, it could be infinite. I cannot draw all, so like it's extending to this side also, it's extending to this side also. And these 4, when I repeat it, I take these 4 and then move it to this unit distance. Then I will get this. When I'll move it further, I'll get this. So this small unit of this whole crystal is what we call unit cell. So unit cell is smallest unit using which we can generate the whole crystal, is what we call unit cell of the crystal. And this generation, for this generation, either we can move it in linear motion, or maybe like if I move it diagonally, this I move to here, this I move to here, okay, and this atom I move here. So all 4 I'm moving in this particular direction, then also I'll get this, right? So the motion, the translation, that we'll discuss about translation and other things maybe next week. But right now, just to tell you, unit cell here is important because just repeating it, we'll get the whole crystal. So we talk about this smallest repeating unit, we call it as unit cell. This is for 2D, so I have unit cell also 2D. If I am talking about 1D, like my atoms are like this, then maybe this is my 1 unit, and then by moving it I'll be able to generate whole chain. Similarly for 3D, now I have X, Y, Z, and this cube that you can see, which contains 4 atoms at top, 4 atoms at bottom, right? If this unit cell, let me highlight, oh, this purple actually, but if it's not clear, let me highlight this cubic box that we can see. If I repeat it backwards, I'll get this. If I repeat it to right side, I'll get this. And so using this cube, I'll be able to generate this whole crystal. And this smallest unit using which I can do so is my unit cell for this 3D crystal structure. And in nature, actually, always everything is 3D. Even though we think it's very thin, only length and width is very, like if we take a sheet. For us, maybe that A4 sheet is look 2D, but we know the thickness is significant enough. There will be a lot of number of atoms arranged. So basically, actually in nature, things are 3D. But sometimes for ease or keeping things simple, we go to understanding 1D or 2D things in 1D or 2D. Okay, so I hope you guys understood what we mean by unit cell of a crystal. Yeah, so next thing comes, this again I think will be discussed later, but just to mention, many times there are questions on this also. What do we mean by primitive and non-primitive unit cell? So like here you saw, I'm calling this a unit cell in 3D. This is also a unit cell in 2D. Now what happens, you can see this is one unit cell, this is another unit cell. Same thing, just like it's like say it's made up of 3 unit cells or something. So this unit cell is sharing this atom, right? In fact, it's better, I mean, this atom does not totally belong to this unit cell. Like say this atom does not completely belong to this unit cell. Why? Because it's part of this also, it's part of this also, and it's part of this also. By this I mean the whole cube, not only the plane, but this is common between all these 4 unit cells. Okay. Oh, so that means contribution of this atom to one unit cell is 1 by 4 here, because it's being shared by these 4. Okay. So here let's take case of 2D to understand this primitive unit cell concept. So I have 2D lattice arrangement and this is my unit cell. Say when unit cell has only one atom per unit cell, here you see this will be shared because there will be another unit cell here, there is another unit cell here and another unit cell here. Since it's 2D, so only these four, it will be shared between these four. So this is being shared by these four. So its contribution in this unit cell is 1 by 4 because it's being shared by 4. So its contribution to this first unit cell is 1 by 4. Now contribution of this atom also is 1 by 4 because again this will be shared by 4 others, right? This will be shared by this, this and this. The same will be the situation for this atom. The same will be the situation for this atom. If you see clearly, all these 4 atoms for unit cell 1 are being shared by total 4 atoms. That means each atom is contributing only 1/4 to this particular unit cell, and there are total 4 atoms. One atom is contributing 1/4 and there are total 4 atoms. That means in this unit cell, number of atoms will be 1. So we have only one atom in this unit cell. That means it's a primitive unit cell. Whereas if I see this, okay, this is also a unit cell. You can repeat this and you will keep on getting, like again I said, we can extend it to infinity. So when you will see, if you extend this unit cell in different direction, this I have already drawn, otherwise it would be better to see something like this. When we'll draw, we'll see this is also a unit cell because after repeating this in all directions, I'll be able to get this lattice arrangement. But here again you see this atom is being shared by 4 unit cells, so its contribution is 1/4. Okay, for bigger unit cell, so this was for smaller unit cell. Here bigger is just for naming them. I'm saying it's not important that it has to be a bigger one, I mean for to be non-primitive, but just here for differentiating. So the bigger one that we see here, it has all the corner atoms are only giving 1/4 of contribution. So 1/4 of contribution, and total they are 4 at the corners. So corner atoms are contributing and giving 1 atom per unit cell, but there is 1 unit cell at the center of this rectangle as well, and that is completely inside this. It is not being shared by any other unit cell, right? Like this one is entirely inside this unit cell. It is not being shared, and this is 2D. Okay, that means there is contribution by corner atoms. They are sharing 1/4. So in total we have 1 atom from corner and we have 1 completely inside the unit cell. So in total number of atoms will be 1 plus 1, that is 2 atoms per unit cell. So this is not a primitive cell. It is called non-primitive unit cell. Okay. So we can take any way actually. Even if we take this unit cell, okay. Now you can see there is no atom inside. So maybe you can think that this is primitive, but we have to calculate. You have to calculate if the contribution of total atom is more than 1, then it's non-primitive. If it's less than 1, then it's primitive. And in this case, if you generate it again, okay, no, not at the center, at the corner and at the edges, then again the contribution from corner ones will be 1/4, so total 1. And on the edges, they are half-half. So we'll have 1 extra atom. So even though there is no atom inside, but still it will be non-primitive if I'm taking this as the unit cell. So I hope this is also clear. And yeah, as you can see here, this is also example of, these are primitive unit cells, hexagonal, that we'll see what is hexagonal and other thing, but this is also primitive. And they are being shared by 3, and the contribution will lead to 1 atom per unit cell, whereas here it's non-primitive. Okay, so yeah, this was just the same thing, that when we call it unit cell, when using that we can generate our whole crystal. These are lattice points. We can associate our atoms or bases at these lattice points, and we get this term called unit cell, which when repeated in all directions gives crystal lattice. And again, it doesn't need to be single type of atom like these black dots. It can be a group of different atoms. Okay, so unit cell I think is clear. Now we'll get to types of unit cells. So in simple, like we have been discussing about unit cell, like building block of a whole crystal. So one just now we discussed will look something like this. This is called simple cubic because all the atoms are at the corners. It has been just named simple cubic. So all the atoms are at the corner. And as you can see, they will be shared by, like if you'll see this one, because it's 3D now. We were talking about 2D, contribution was 1/4. Now if you'll see here, because this atom is being shared by, I hope you can see, like this plane, then this plane, this is the third plane, and this is the fourth plane it is being shared by. Then these are 4 at the bottom. Now these are 4 at the top also. So this unit cell, even it's part of this and part of this, and these two as well. So 4 unit cells at top, 4 unit cells at bottom. This one atom is being shared by 4 unit cells at top, 4 unit cells at bottom. In total 8 unit cells. So in 3D, when we are talking about simple cubic unit cell, we see one atom is being shared by 8 unit cells. I hope this is clear as well. If you have any doubt, you can ask, I'll explain again. So it's being shared between 8 unit cells. So its contribution in one unit cell will be 1/8. Okay? Like in 2D, it was 1/4. In 3D, it's 1/8. I hope this is clear. Okay, so this happens in simple cubic unit cell. Now the same cube we have, but when, let me first draw. My drawing is not very good here using this digital pen, so please don't mind. But if it's not clear, then I'll try to make it better. But here I think it's okay right now, right? So when in a unit cell, we have atoms at all the corners, and we are just talking about unit cells, but we know it's ultimately part of a crystal. So it's surrounded by other unit cells all in all directions. So keep in mind always it's being shared by 7 other unit cells. So we are just right now focusing on one. So when we have unit cell like this, with atoms arranged at the corners, and then one more atom arranged at the body center. Now it may be difficult to visualize here when I'll draw because this is 2D screen, but just think of a cubic wooden box, and inside you have kept a ball. So that ball is completely inside. That's what I want to show here. Maybe I can choose some different color. Let me try. So inside this cube, there will be a atom. It's not on any particular face of this cube, okay? It's very much in the center of this. When this happens, then we call it body centered. And as the name very much tells, because it's at the center of this body, which is a unit cell. So this is called BCC or body centered cubic, because this is also cube, this is also cube. So simple cubic or body centered cubic. Simple cubic crystal or body centered cubic crystal, a unit cell. And then we have FCC. Okay, in this we have everything, not everything, we have 8 atoms at 8 corners, and then we have in a cube, if you remember or you can visualize, in a cube we have 8 corners. So these corner atoms are arranged at all these points. Then number of faces are 6, right? So now in face centered cubic we have atoms in the center of every face. Okay, so top face, bottom face, right side face, left side face. Now what is left? Front. If I'll draw it will get very confusing, but front side will have one more atom, and back face will have one more atom. The front face and back face. So total 6 faces, so total 6 atoms. And these corners we understood, they contribute 1/8. These faces, if you can visualize here, that if I have in this unit cell, okay, at the back plane, if I have an atom, then it will be shared between this front and the back unit cell. So its contribution becomes half. So all this face centered atoms contribution is half to one unit cell. Okay, so these are the very basic type of unit cells. Then it's been found out by scientists that there are total 17 type of crystal systems, and scientist Bravais said that even in hello, okay, so there are basic 7 types of crystal systems using which we can generate all types of materials that we see in nature. Is someone saying something? If not, then please keep your mics muted. Okay. So these are 7 type of crystal systems, and then further, when we have different type of atom arrangement under these systems, then we get Bravais lattice, which are 14 type of Bravais lattices. This is for 3D systems. Like we saw just now, I'm calling it, we understood the simple body centered and face centered when we were talking about cubic crystal, right? How we define cubic crystal is when all the 3 sides or 3 axes are of equal magnitude and the angle is 90 degree. Okay, so let me explain. When we have a cube, the unit cell, okay, one axis, x-axis, another axis, y-axis, and this is z-axis. Okay, when this the one side of the box, like along x-axis, along y-axis, usually we call B, this is C. Okay, along y-axis, and the side of the cubic box along z-axis, along all 3 axes when the sides are all equal. Okay, and now to understand what do we mean by, so A, B, C. Now the angle between x-axis, the angle between x-axis and y-axis is called gamma. The angle between y-axis and z-axis is called beta, and the angle between z-axis and a-axis is called alpha. Okay, so we say the unit cell system is cubic when all sides are equal and all these angles between them is all equal and equal to 90 degree. Like we talk about this cubic crystals that we just discussed, simple cubic, body centered cubic, and face centered cubic. Here all sides were of equal length and all angles are 90 degree to each other. So this is example of cubic system. Okay, In that we discussed, because the arrangement of atom was different, so we got three type of Bravais lattice under cubic system, which was simple, body centered, face centered. Then we have tetragonal, another type of crystal system, where the angles are all equal and 90 degree, but the sides are of different length. Under that also we have two type of Bravais lattice, simple and body centered. Similar way we have in total these 7 type of crystal system, and depending on the difference in atomic arrangement, in total we have 14 Bravais lattice. And these things we, I think, can discuss in detail when we will be talking about symmetry. There is something known as symmetry. That time again we will discuss. So right now we don't need it much, but just to make you aware, these are the for 3D when we are talking about crystal system are of 7 types, and in total 14 Bravais lattice. Okay. And yeah, this is just with the figures. So right now what we discussed was the 3 Bravais lattice of cubic crystal system. Okay. Okay. So now after understanding these type of unit cells, what are the different properties we can study or we need to know when we are talking about any kind of unit cell? So here again we are just considering and talking about cubic unit cell. So in cubic unit cell, we can first try to find out number of lattice points per unit cell. This just before we were discussing that in 2D also we had seen. If I take you back here, here we were discussing that in 2D that one atom is being shared by 4 cells. So then we calculated how much is total number of atom for one unit cell. Similarly, we did here for 3D, when a unit cell is being translated and it's generating the whole 3D crystal structure, then the corner atom is being shared by total 8 unit cells, so its contribution is 1/8. So in that way, for a simple cubic unit, what is the number of lattice points per unit cell? So lattice points also, either we can say about atom or the lattice point. Okay, the lattice point also is where we place the atom. So these are the corners where we keep the atom. So this is the lattice point. So either you can say number of lattice points, or again, like why we usually don't say number of bases per unit cell, because there could be more than one atom per lattice arrangement. I hope you understand. So either we can say number of lattice points per unit cell. So, but the calculation is same, that in 3D every atom will be shared by 8. I'm just drawing the top of these unit cells, and similarly 4 unit cells will be on the top. So this one atom or one lattice point will be shared by 8 unit cells. So contribution of these corner atoms, corner lattice points, let's stick to one term, corner lattice points, their contribution in one unit cell will be 1/8. And we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 lattice points for one unit cell. So total number of lattice points for one simple cubic unit cell will be 1. Okay, this is for simple cubic crystal, so SCC, or body centered cubic unit cell. Now, so here we have, in this unit cell, we have lattice points at the corners and then lattice point in the body center. So from the corner atoms, the contribution will be 1/8, and again at the corner number of lattice points is total 8. So from corner we have one lattice point in total, and then one is completely inside. So one from that. So in total 2 lattice points per unit cell. Per unit cell in the case of BCC. Now for FCC, just earlier we discussed all the corner lattice points will lead to one lattice point, and then we have at face, every face, there are total 6 faces of a cube. That means we have 6 lattice points, and every lattice point is contributing only half to one particular unit cell. So it will be 3. So total number of lattice points will be 4. 4 lattice points per unit cell in case of FCC. So this is the information we should keep in our mind, that number of lattice points from simple cubic crystal is 1. For BCC it's 2. For FCC it's 4. And this will help us further in doing some other, when we'll try to find out some other information out of a unit cell. Okay, next is to find out the volume of unit cell. Okay, so volume of unit cell, to find out the volume of unit cell, we, like here we did, or let me tell you. So when we want to find out volume of unit cell, like if I draw it again to show you, okay, it's okay. It's difficult to draw it like this. Change the color back to red. So when we talk about this cubic unit cell, these are all at 90 degree to each other, right? And this I'm saying is y-axis, and this is x-axis, and this is z-axis. Okay, and this unit length, the length of the side of this crystal, along x direction we call it A, along y direction we call it B, and along z direction we call it C, the length. And if it's cubic, then A is equal to B is equal to C. Okay, so when we want to find out the volume, first we will take, let's say this is vector. Okay, so it's A cross B, which gives us area. This A cross B will give us the area, and since A and B are vectors and we are taking cross product, that means we will get some unit vector with the magnitude, and that will point towards the direction perpendicular to this area. I hope you know we call something as area vector, right? Area vector is perpendicular to its direction is perpendicular to the plane where that area we are talking about. So we are talking about this plane which is an xy plane, and the vector of this plane will be along z direction. So this will be some z. This will be some z. Now after taking cross product, when we will take dot product with C, this will give us some vector, and when we will take dot product with another vector, we will get this whole volume. And if all these are equal, then we'll, because usually it's AB sine theta, and here we know the angle between A and B vector is 90, sine 90 is 1, so it will be AB and some unit vector, and its dot product with C, and if A, B, C all are equal, that means A dot A dot A, like cube. Okay, and dot product of two vectors gives us magnitude, just a scalar, not a vector. So it will be A cube. Or if they all are different, but the angle between them is 90 degree, because this dot product gives us cos, right? Cos theta. And this unit vector is along C, so the angle will be 0, cos 0 is 1. So A cube. If they are equal, if they are not equal, then A times B times C. But eventually we will get the volume. So to get the volume of a unit cell, the formula is A cross B dot product with C. This gives us volume of unit cell. Okay. Now moving on to another information that we can find out from a unit cell is lattice point density. What we understand by lattice point density is we denote it by this. This is the symbol rho we use to talk about density many times. And here we are talking about lattice point density. What this means is number of atoms in the unit cell divided by the, because density, this is what we mean. By density, usually when we talk about mass density of any body, we talk about the mass and then divided by volume to tell this is the density of this object. So here when we are talking about lattice point density, we will see number of atoms for that unit cell and then volume of that unit cell. Number of atoms in unit cell and volume of unit cell. Okay, this is the formula. Now what will be the number density for SCC crystal, SCC unit cell? In simple cubic structure, we just saw in simple cubic, number of lattice points or number of atoms will be in total contribution for one cell will be 1. So for simple cubic crystal, lattice point density will be number of atoms in unit cell is 1, and let's say it's cubic, then volume will be A cube. Now for BCC, number of atoms in unit cell is, as you can see, 1 contribution total from corner atom and then 1 from the atom completely inside. In total 2 lattice or 2 atom per unit cell. So 2 divided by A cube. And now for FCC, what will be the lattice point density? Number of atoms or number of lattice points for FCC unit cell will be 4 per unit cell. So number of atoms will be 4 per unit cell divided by A cube. So these are the values for lattice point density when we talk about simple cubic, body centered cubic and face centered cubic. Okay, this is one thing. Now let's talk about packing fraction, another very important aspect that we talk about. So let's try to calculate packing fraction for simple cubic and we'll understand what we mean by packing fraction. So like again, it's better to see here. So like this is an example of simple cubic, right? All the atoms are only at the corner. Now by packing fraction, what we mean is that we have been saying so many times that the atoms are at the corners are only contributing 1/8 because they are being shared by 7 other unit cells. So, and ultimately that leads to 1 atom in 1 unit cell. So we want to find out that atom, volume of atom divided by volume of unit cell. That ratio will give us how many atoms are actually there in that unit cell, how packed that unit cell is. Let's try to understand this further. Yeah. So in simple cubic, although for ease to see the unit cell diagram clearly, we just draw very small points and we say this is our atom. Okay, we very conveniently represent it like this, but actually the atoms are not this small compared to the length of unit cell. So how they actually look is something like this. If I just draw the front of this unit cell for ease, I'm just seeing it from the front, or I'm just drawing the front of this unit cell. And in reality actually, so my atom is not this small. Okay, we draw this, but atom is not actually this small. In fact, I'll take another color. The atom is The radius of atom, we know it has some radius. It's not like a atom is not a point, it has some finite radius. So for simple cubic, the atom arrangement is like this. Okay, this is one atom at this lattice point, then another atom at another lattice point, and then another atom at another lattice point. These are all spheres, of course, atoms are spheres. And this is the way they actually arrange. But if we'll draw all this big size thing, then we'll be not able to see clearly all the position. That's why we usually represent it with small points. But actually, the atomic arrangement in unit cell is this. Okay, I hope this is clear. So here we can see the radius of this atom, since all atoms are same, so all radius is also same. And if this radius, I didn't change the color. Yeah. If the radius of atom is r, and this is the side of unit cell, right? This is the side of unit cell. This that we talked, we can find out the volume of unit cell for simple cubic or for any cubic. If its all sides are equal, then it will be a cube. So this is a, and we can see this a is equal to 2r, right? Radius of this atom, radius of this atom, because this portion is not inside this unit cell. I hope you can, when you will draw like this, only 1/8 is inside this unit cell, remaining is in another portion. So when you will see only this plane, you will see only 1/4 is here. This other 1/4 will be on top unit cell, this another 1/4 will be in another unit cell. So like if I'll see, what I want to say, if I'm seeing from top, then my one atom is being shared like this. 1/4 contribution here, 1/4 contribution here. This is only when I'm seeing these 4 planes. Now there will be 4 unit cells on top of these unit cells. So in total it's contributing only 1/8, 1/8, 1/8, 1/8, and then 1/8 to such same unit cells on the top of these. So here this is the only what is getting contributed here. But okay, so to find out, that's why we want to find out what is the packing fraction of this unit cell. So I hope you understood. This is the edge, the unit cell side length is A, and A is equal to, because these spheres or these atoms are touching each other, so their radius of this atom, radius of another atom is equal to the length of this unit cell. So this way we found out the radius of the atom is A by 2. Okay. Now I told the packing fraction is defined by total volume of atoms in the unit cell divided by volume of unit cell. Okay. Volume of unit cell is what? A cube. Now, what is the volume of this sphere atom part which is inside? So we know all atoms contribution in one unit cell is 1/8, and their total number 8 atoms because there are 8 corners. So total 1 atom is there inside. Okay. Now, how to find out this volume of atoms in unit cell? We know that in total there is only 1 atom in the unit cell, and since atom is sphere, so we'll use the formula for volume of sphere. This is the volume of 1 atom, and in total there are only 1 atom in the simple cubic cell divided by A cube. Okay. Now this R and A. Draw more slide. Let's do this. Okay. So now when I here I'll substitute the value of r, because we just now found out the relation between radius of atom and the unit cell edge. I'll substitute that value here, and packing fraction, in short, it will become 1 is the total number of atoms, and volume of one atom 4 by 3 pi r cube. Okay, let me write once. R cube divided by A cube is the volume of unit cell. Now R we know is A by 2, right? We deduced the relation here. So R is A by 2. When I will substitute this relation here, I'll get 4 by 3 pi, and this will be A cube by 2 cube by 2 whole cube divided by A cube. This A cube will be cancelled, and we'll be left by 4 by 3 times pi 1 by 8. So this will give us pi by 6, and when we'll do this pi by 6, we'll find out the value 0.52. If I want to put it in packing fraction in percentage, then it will become 52%. So this, see, half of the volume in simple cubic unit cell is empty. Only 50% is occupied by these atoms. This we get to know when we find out the packing fraction. Now let's do the same for BCC. Okay, we have so body centered cubic. Here what happens? Again, if I'll show you one good figure so that you don't get confused. So body centered is like this. We have some atoms at the corners, their contribution is 1/8, and then we have one atom completely inside, so its contribution is 1. So in total for BCC we have 2 atoms per unit cell. Let's use this information here. So we have 2 atoms per unit cell in the case of BCC. Now what is the relation for BCC between radius of atom and the unit cell edge? Okay, so what happens in BCC, again, like I told you in case of simple cubic, that the atoms are not simply arranged at the corners, they are touching each other. The same thing happens for BCC, but like how they are touching each other, let's see. So here what happens, there is, okay, I want to tell you there is something like, okay, let me draw this unit cell again. Okay, this is unit cell. Now if you see carefully, let me again change the color. If you see on this plane, let me call it A, B, C, D. I'm talking about this plane, okay? In this plane, we know we have something called phase diagonals, right? And then there is, if you see this from A to, let's call it X, like this corner of the unit cell, from this corner of unit cell, if I join this back side of the unit cell, like this point is on the front plane and this point is at the back plane, and they are opposite to each other. When I join these two atoms or these two lattice points, we get something called body diagonal. So this ACBD is phase diagonal. You need to understand this because we need this information, this clarity to calculate packing fraction for BCC. Okay, so ACBD is phase diagonal for this phase. Similarly, we'll have BX and CY will be phase diagonal for this phase. Similarly, for all the 6 phases, we have phase diagonals. Every phase has 2 phase diagonals. But AX, or if I'll connect this Y with this point D, if I connect Y with D, that will be a body diagonal. If I connect this point, let's say Z, with C, it will be another body diagonal. Okay. Why I'm telling you about body diagonals? Because now my atoms will be touching not along this edge but along the body diagonal. So now, because I told you in BCC I have atoms at corners and at the center, but they are touching. Okay, so if I take this AX diagonal, then the situation is like this. The center one is there completely on this body diagonal, and now the corner one is like this. Oh, they're very bad diagonal. I'm sorry. I don't know, the eraser will help. Oh, okay, anyways. Yeah. So now the situation is like here, from the center of this to the center of this. So this is my A and this is the X point, and the body diagonal, again sorry for the drawing, but these are touching each other. Okay, these atoms are touching each other, but they are not touching at the edge, they are touching here. So now I want to find out packing fraction using this body diagonal. So what happens, this side is A, this side is A, and they are at 90 degree to each other. So this triangle, this phase diagonal distance will be what? Like here ADC, if you consider ADC triangle, we know from Pythagoras theorem, right? That is very basic. This is because this is 90 degree. So we know this is A, so we can say this is root 2A, right? A square plus A square is equal to AC square. So AC will be root 2A. Now what will be the body diagonal length? This is another question. To help you, I can directly tell you as well, but just to help you out with the maths, I have this already written here to save some time. So right, we were saying this green color here is a phase diagonal. You can see this lower one plane, okay, it's connecting its two opposite points, so it's phase diagonal. Whereas this blue, so the green line here, just to clarify, the green line here represents phase diagonal, and the length of phase diagonal is root 2A. How? This, like the BC square, which is the phase diagonal, its magnitude will be BD square plus DC square. So BC will be root 2A. That we understood. Now, what will be the length of this body diagonal AC? To find out that, we know this is also 90 degree. So we'll apply Pythagorean, that AC square, which is the length we want to find out, let's call it small d. So d square will be AB square plus BC square. Okay, just simple Pythagorean. And now this AB is small a and this BC is root 2A. Just now we found out. So using one phase diagonal length and this edge length, so what this means is A square plus root 2A whole square. So this will be A square plus 2A square, that is 3A square. That means this D is root 3A. So this was just to give you a way how we find out, just instead of just giving you the length. This is just so that you understand how we get this value. Okay, so I hope you understood this. Now we'll directly use this, that length of body diagonal of a cube is root 3 times the lattice, the edge. So that information we'll use, that this length AX is root 3 times A, and it's equal to how many radius? This is R, this is R, this is R, and this is R, because it's all the same atoms. Yeah, my drawing is bad, I'm sorry. So the size looks different, but they are all the same atoms. So in total, this root 3A is equal to 1, 2, 3, 4. This is equal to 4R. That means radius will be root 3A by 4. Okay. For simple cubic, relation was different. Now for body centered, relation between radius and edge is different. We'll use this, and when we again, let me take one slide. Yeah, using this relation, when we'll substitute packing fraction, will be, so number of atoms for bodies BCC is 2, so 2, and volume of one atom is 4 by 3 pi r cube. Now r is equal to root 3a by 4. So I'll take this value here, root 3a by 4 whole cube, right? This is my radius, divided by volume of unit cell, which is a cube. So I'll get 2 times 4 by 3 pi. When I'll take cube of root 3, I'll get 3 root 3. This will be a cube, and this will be 4 times 4 times 4. Okay, and in denominator we'll have a cube. This a cube will get cancelled, this 4 will get cancelled, this 3 will get cancelled, this 2 will get 2. So ultimately what I'll get in numerator, we'll have pi, and we'll have root 3, and then we'll have 2 times 4. That means root 3 pi by 8, which when we'll do using calculator, we'll find that the value is, for this we get the value is equal to 0.68, and in percentage it will be 68%. So we can see that the packing fraction is somewhat better than simple cubic. Simple cubic had half, like half of it was full of atom and remaining half was empty. In case of BCC unit cell, more than 50% of the unit cell is occupied by the atom, by the volume of atom. Now let's see for FCC. Okay, so packing fraction for FCC. Now here what happens is the closest packing is between the atoms on the face. Okay, again when we draw it like this, right? We draw it like this, but in reality when the atoms are touching, they are touching each other like this. Okay, but this time you can see this is not body diagonal, this is face diagonal. Okay, it's not body diagonal, it's they're touching along the face diagonal. And then there is another atom here, and then there is another atom here. So these three are touching, which are along the face diagonal. Now face diagonal length, we had seen face diagonal length is root 2a. Face diagonal is root 2a, and radiuses are 4r. So r in terms of a will be root 2a divided by 4, which is a over 2 root 2. When we will substitute this and try to find, okay, so what is number of lattice units or number of atoms per unit cell? This we have done several times, that for FCC, number of atoms per unit cell is 4. 1 from all the corners and 3 from all the faces. So 4. Okay. Yeah. So when we want to find out packing fraction, number of atoms is 4 and volume of one atom is 4 by 3 pi r cube. Now r is this, that means a divided by 2 root 2 whole cube divided by a cube, volume of the unit cell. Okay, let me simplify this. This will be 4 by 4 pi by 3 a cube, cube of 2, let me write like this. Okay, and then root 2, cube of root 2 will be 2 root 2. and then in division we have AQ. This will get cancelled, and this 4 and this 4. So we will be left with pi by 3 root 2. Okay, and this pi by 3 root 2, when we will see this is equal to 0.74, and in percentage will be 74%. That means we can see that the packing fraction of simple cubic is very less, packing fraction of body centered is more, packing fraction of FCC unit cell is even more, 74%. So this is another information we can find out from type of unit cells. Okay, so these were, now we have to move on to finding out coordination number, another very important property whenever we talk about any kind of unit cell. So let's, here as you can see, this is a 3D crystal arrangement, and this one is one unit cell. Now we want to find out, first let's understand what do we mean by coordination number. Whenever we have any kind of unit cell, we want to know which, like if we take any atom in this unit cell, like this is my unit cell, and I take this corner atom, I want to find out which is the nearest atom to this atom and how many such nearest atoms are there in this crystal. Okay, that is what we mean by coordination number. The number of nearest neighboring atoms to that particular atom is its coordination number. So for simple SCC unit cell, since all the atoms are at corner, so coordination number will be coordination number for any of the unit cell. Let's take this one, which is being shared by 8 others, of course. Now to it, actually all are only at the corners here, and then if I extend this, I have something like this, 4 at the bottom, 4 at the top. Now every atom is being shared by 8, we know that. So its nearest is at a distance, okay, because the other one, if I see, this is in one direction there is one atom, in this direction also there is atom, but the distance, we know this face diagonal distance is root 2 times a, that means some 1.44 something times a. So this is at a little more distance. So at this direction, the another atom is at little far. So this is definitely not the nearest neighbor, right? Coordination number includes nearest neighbor, nearest neighboring atom. So this atom, which is at face diagonal distance, is not the nearest. Which is the nearest? This one, which is at distance a, because there is no atom closer than this distance here. So now we understood a is the minimum distance. Now how many atoms are there for this particular atom which are at a distance? So there is this one, then this one, then this one, then here, then similarly there will be 4 down, 4 like up. Like if you see this corner, there is one here, like one here, the same 4 will be up. It's better to see here because it will be difficult for me to draw. So this one atom is being shared by these 8 unit cells. If I take this one corner atom, then there is one at the top. This is also at a distance. This is also at a distance. Let's say it's 2. One at top, one at bottom. Then one at front, one at back, one at left side, one at right side, and one at left side. They all are at a distance. Okay, they all are at a distance with this orange atom. I mean, they all are same atom, but they all are equal distance, and so they all are the nearest neighboring atoms for this. So the coordination number for SCC unit cell will be 6. The coordination number is 6. Okay, this is how we find out the coordination number. Now moving on to find understand coordination number for BCC. So again, I have searched on internet and brought this diagram for you because it's get difficult to draw here. So here if you see this purple atom, we have this unit cell. Again, it's surrounded by same unit cells because it's the crystal. The same unit cell repeats to generate this whole crystal. If you focus on this purple one, then you will see the minimum distance is this, which is actually root 2a by 2, because we know root 3a by 2, because face diagonal distance was root 3a and half of it, so this is root 3a by 2. So this 1, 2, 3, 4, these 4 on the top plane are at equal distance, right? And these 4 at the bottom are at equal distance from this. So it's like in simple units, if I just draw one unit cell, okay, what I'm saying is in BCC I have all the atoms at corners, right? All 8 corners, and then I have one at the center. I have atom 1, where is it? Yeah, I have one atom at the center. Now all these 8 atoms are the nearest neighbor for the center one, and they all are equal distance and they are the nearest one. So this one, the second, third, fourth, then fifth, 6th, 7th, 8th. Maybe it's difficult to see in this 2D structure, but these these all 8 in this BCC are the nearest neighbor for this center atom. So the coordination number for BCC is 8. Like see, they have shown the nearest neighbor is 8, these yellow one. Then next nearest is these red ones, but they are far away. They are not the nearest one. Then after that also next nearest is this green one. But coordination number is the nearest neighbor only. So coordination number here is 8. I hope you understand. Now FCC, it's a little tricky, but let's see. So in FCC, I'm showing here again the structure will be something like this because the unit cell is repeating in all x, y, z direction. But here, to keep it simple, I'm just drawing 2 unit cells, and in this one unit cell, this is one face, okay, then one on top. I mean, of course, at the corner, I'm just not showing to keep, it's not drawn to keep the picture simple. Otherwise, it's FCC unit cell means all the corners have the atoms and all the faces have the atoms for both, okay? All the corners, all the faces have atoms. Just to keep things simple so that we can finally see which one is the nearest one, we have not drawn all atoms here. So now we want to focus, let's take this one which is being shared by these 2 unit cells and let's see which is the nearest neighbor. So these corner atoms are the nearest neighbor here, okay? And then same way, the next nearest is this one. This actually makes a plane here. Very bad drawing, sorry. See. So the distance between this is, we know it's face diagonal, and half of it means this is root 2a divided by 2, because this is the length of face diagonal and half of it, which is a divided by root 2. The same is the distance between this and this atom, the faces of these two, right? The atoms is on face of this and we are connecting it to face of this atom. They also have same distance. The same way, this also has same distance. This atom on this face is also nearest, atom on this face is also nearest, and actually they also form a plane. This is what I was trying to tell. Because this plane that I am Anyway, I think we'll understand it later, it's okay. But these atoms are all the nearest. So the coordination number becomes 12. We'll discuss later what do we mean by plane. It's again not something physically, but when we have arrangement, like if I see this from one side, FCC unit cell, if I just concentrate on it from one side, then I'll see this plane, because the atoms are in one plane. They are not up and down. I mean, they are at same plane position, either XY plane or YZ plane. So that's why we call it one plane. So the same, these four atoms I'm seeing, they are all in same plane. So they are at equal distance. Again, this one is at same distance. They are at same plane. So FCC will look like this, right, from one side. So this is what I wanted to tell. So coordination number for FCC is 12. Okay, now, yeah, the topic comes about crystal planes. So just now that I explained that whenever we have any arrangement of atoms and crystal, because arrangement of atoms on lattice points gives us crystal, and the building block of any crystal is a unit cell. Now in that crystal, like any here, let's see, or maybe some way if I have some better diagram just to see where, yeah, like maybe if you see here, this is a big crystal, right, and this dark, which is drawn with this dark shade, is one unit cell. Now this is the top of all these four unit cells. If you see, like this is one plane, all the atoms are lying in this plane. Then parallel to this plane we have another plane which is parallel to this. This also has same number of atoms. Then at the bottom also we have plane in which same number of atom is there, and all these three planes are at, they are same actually because they are same distance also. So this is what, this is a crystal, this 3D structure, okay, with all the atoms at particular distance and forming pattern, and this plane in which the atoms are, that is called crystal plane. Now this crystal plane is not only horizontal. If you see, like if I see this, now here I was focusing on the horizontal plane. If I see the vertical plane also, then I see vertical plane also exists, and they are also parallel to each other, right? And even diagonally or slanted. So there are various way in which there are planes existing in this crystal, and they are called crystal planes. Okay. Now before understanding much about crystal plane, let's see, maybe we can first start doing some. So I think for this session, just understanding that the crystals, when we focus on one side, we get something known as planes, which again is a mathematical thing, because actually only atoms at same position are there, that we call a plane. And now we'll see how there are other things related to this knowledge of crystal planes. Okay, that is called Miller indices. Whenever we talk about crystal planes of any crystal, we talk about Miller indices. What do we mean by Miller indices is that whenever we have any such crystal and we are talking about this, like if I'm talking about this plane, so what to call this plane? So naming these planes in a way is what we do by using Miller indices. Okay, so let's see how we do. Now I think we can start by doing the assignment problems, because yes, we have some time left for today's session. So let's focus on the assignment problems, and there I'll tell you how to find out and what do we mean by Miller indices with the first question itself. So basically just try to understand when we name these, and how it looks, I'll tell you. Miller indices for crystal plane is something like this. We have three integers inside this parenthesis. This is what is Miller indices. So 100, or 210 or 200. So some plane will be called 100 plane, some plane will be called 210, some will be called 200. That depends on the fact that the plane doesn't need to be a square also. Let me show here. If I have x, y, z, okay, these are the three axis ordinate, crystallographic axis that we know. And then if my plane is forming any angle with these three, if it's a square or maybe the plane is of this triangular shape where at x-axis it's intersecting here, at y-axis it's intersecting at this point, and z-axis it's cutting at this point. So the plane could be, yeah, it's not like it has to be a square. Anyway, these are like infinite and they get this shape because they are cutting these axes at this portion, at this portion, at this portion. So when I'll see this. Otherwise, plane means like it's infinite. Only when it's cutting these axes in this angle, then I see like it is like this. If it's that infinite plane is cutting along, say this is x-axis, it's y-axis, it's z-axis. Say it's cutting like this. Okay, it's cutting x-axis at half and it's parallel to y-axis, it's parallel to z-axis. Then like this is infinite, I see here like this. So it's not like the plane is square or rectangular, it's just how we can visualize it. Otherwise the plane is like a plane, infinitely big plane. I hope I didn't confuse you there, but anyways, okay, so let's focus on the assignment problems now. So first question we have is determine the index for the direction. Okay, so with the plane, another thing is all these planes have associated direction also. Like if you I hope you remember when we were finding out the volume. Yeah, I had told you first we take the area and then we multiply it with we take dot product with third vector. So this and I told you area vector, the concept of area vector, that we have a area and perpendicular to it is the direction of it, which we call area vector. Okay, so here also when we were talking about plane, okay, when we are talking about these planes, so perpendicular to these planes also we have something known as direction. That also we'll discuss now. Or otherwise also, if I'm just talking about that, like see, for example, this is my atom position, this is say x-axis, this is y-axis, this is z-axis, and I want to find out the direction of atom B from atom A. Then this is the direction. I just want to name what is this direction. So any kind of direction, it could be from this atom to this atom, or this atom to this atom, or this atom to this atom. So we want to find out how to know the direction when we are talking about crystallography. So these axes, which we have already studied in mathematics context of that every 3D space has three axes x, y, z. Here we say call them crystallographic. Let me not do it here. Let's come here. Here we call them crystallographic axis. It's the same x, y, z. Okay. Okay, let's start with the first question. So the question is, determine the index for the direction OP. This is a unit cell, looks like a cubic unit cell. O is a point. This is x, y, z. Also, I want to tell you one thing, that usually how to take the direction, like it's not, we should not randomly do that we take x here, y here, or z here. Okay, because one standard way of doing this is we keep it in anti-clockwise direction. We always follow anti-clockwise direction. So what we do is x, y, z. You can also write it like this: x, y, z. You can also start x from here and then y from here, z here, but don't do reverse, because here it's not anti-clockwise, here it's clockwise. So the standard way is we follow to keep uniformity is, after we have chosen our x-axis, then y-axis has to be anti-clockwise, and then z-axis will be anti-clockwise to y-axis. Okay, this was just another information. So here this is x-axis, this is y-axis, this is z-axis, and this is our O. Like, again to clarify, you remember when we do some graph thing, and this is our positive axis, this is our first quadrant, this is our second quadrant, this is third quadrant, this is fourth quadrant, and this is our origin, and we say this is 0, 0, right? So here we have something in 3D now, and this also needs the origin. So this is 0, 0, 0. This O here represents 0, 0, 0. This will be the coordinate of this O, which we call origin. And then other points will also have this 3. So in 2D we used to have 2 points, x and y. In 3D we have x, y, z. These 3 coordinate information. So origin has 0, 0, 0. Okay, so now we have to find out the index for the direction OP. OP is a direction that starts from the origin, ends at the edge here. Now, how to give the Miller index to this direction? Firstly, what we need to do is, one very important thing is, whenever we need to find out the index for, that is the Miller index for any direction, our direction should start from the origin. It should start from origin, otherwise it will get difficult to understand how it's how to proceed. It gets difficult. So like in this case, it's already starting from the origin, so it's okay. In next questions, we'll see if it's not starting from origin, then we'll shift it to origin, and that there's nothing wrong in it. Only it should be parallel. Wherever we are shifting, it should shift to parallel. That's it. I think if you remember, we have understood in class 11, 12 also, when we were studying about triangular law of vector or rectangular law of vector, we had seen that if I have to add something like this, there is no problem. We can just shift it and connect it here. Only we cannot change is its angle. We cannot change it in different direction. But if I have to add something like this, I can always shift it up, right? And then I know triangular law, or whatever direction it is. Usually we take like this. Yeah. So shifting is possible, only it should be parallel. Okay. But here we don't need any shifting because our direction vector is already starting from origin. Okay. So with all this extra information, now what we need to do, we need to see here what is the intercept of this vector on x-axis. So this is the x-axis. Let me take another color here. So this is the x-axis, right? This is the y, sorry. This is the y-axis and this is the positive z-axis. Please bear with my drawing. And then opposite, like in 2D case, we knew this is x-axis, this is y-axis. So there, of course, has to be minus x and minus y also beyond the origin. Same way in 3D, if at the front of origin is plus x, that means at the back will be minus x, and if this side it's plus y, then if I extend it on another side of the origin, then I'll get minus y. And same way, if on the up I have plus z, then below I'll have minus z. So like in 2D, I had plus x minus x plus y minus y. Same way in 3D, we have plus x plus minus x plus y minus y and plus z minus z when these x's are extended to the opposite side. Okay, I'm just recollecting all this. So okay, so here when I, let me take again another color would be better. It's okay. Okay. So OP here is the direction vector for which I need to, where is my pen? Push. So, okay. Oh, here. Okay. So OP. Now OP, if I take where its intercept, where it falls on x-axis. So when I drop a perpendicular from OP, I'll see it intersects here at half. Okay, let's see, like of course it looks more than half but all the answers have 2 in them, so I'm telling you, like, it's maybe the diagram is not good, but it's, let's say that it's cutting at the half of the edge. Okay, so when I'll drop a perpendicular from the head of this vector to the x-axis, this is my x-axis, then it will be cutting the x-axis on here, along the x-axis the unit cell is A, along the x-axis the unit cell length is B, along the z-axis unit cell length is C. So along the x-axis, when I take the intercept of this vector, it will be A by 2 along x-axis. Along the y-axis, when I take, it will be this up to here, which is 1 times B, right? This whole length. Along the z-axis, there is nothing. Why? Because this vector is completely lying in the xy plane. If I look from the top, I'll see that this is the x-axis, this is the y-axis, and this vector is something like this. This is P, this is O, okay? This is my xy plane. So x-intercept is A by 2, y-intercept is B, but it's completely lying in xy plane. So intercept for z-axis is 0, 0, C. After we find out these intercepts for x-axis, y-axis, z-axis, what we have to do is just like remove this ABC thing, okay? Just keep the magnitude, which is half, 1 and 0, okay? Half, 1 and 0. This is the next step. After this, what we have to do is, we have to simplify this, because we want to ultimately, Miller index always have integer. It doesn't consist of fraction. So we need to make this into integer. How we can do? If you see, if I multiply this with a 2, then it will become integer, and these will also remain integer. Whatever we are doing, we have to do to all 3 numbers. Okay, so if I multiply these 3 numbers with 2, okay, then this will become 1, this will become 2, this will become 0. So, and then for direction we use this bracket. So the Miller index for this direction OP will be 1, 2, 0, 1, 2, 0, okay, with this bracket. When we talk about planes, we use this curly bracket. When we talk about direction, we use this square bracket. So this is the Miller index. So 120 A is the correct answer. Okay, I hope it's clear. If you guys have doubt, you can ask. Then we can move on to next question. So here, here we have to find out the index, again the Miller index for the direction OA. O is here, origin. This is x-axis. Okay, let me draw. It's not properly drawn. So this is the plus y-axis. This is the plus x-axis. And this the top, it's z-axis, and they are like 90 degree to each other. I think this also you know. If I'm talking about y and x plane, then I know that z-axis will be out of plane or inside, like perpendicular to these two directions, right? Coming out and going in kind of direction it is. So we usually like represent by this dot that it's coming out. And when we represent by this, it means going inside. So z-axis is perpendicular to xy. So here to show all three axes, we draw it in this form, but the angle between all these is always 90 degree here, what we are considering. Okay. So the interested in the direction in which we are interested here is this OA. O and this is A. Okay. Now, as I told you, don't think that the vector is going out of the unit cell. It's not like that, because the unit cell is creating the whole crystal. So it's never alone. Unit cell doesn't exist alone, right? It's surrounded by all the other unit cells, and together they form the crystal. It's just for simplicity we draw one unit cell, but it's always surrounded by other unit cells. So if you see this kind of question, don't think that this is something by mistake they have mentioned because it's going out of unit cell. No, because there is another unit cell here. If I'll draw, it will be confusing, but the same kind of unit cell is there in all directions. So it's just now, instead of putting into this unit cell, they have drawn it in another unit cell. Everything is correct here. Okay, with this, now I told you the first step is to ensure, whenever we have to find out the index for Miller index for direction, the first step was to ensure that the direction vector is starting from the origin. So here also we see this O is the origin, this is plus axis, this is plus y axis, this is plus z axis, and this is the origin where these three axes meet, and our vector OA is starting from the origin. So okay, first step is fulfilled, and so it makes our life very easy. I'll tell you in other questions, when the vector is not starting from origin, we need to do some exercise, because otherwise it won't be convenient for us to find out the direction. Okay, so here it's already starting from origin. Okay, now this OA, we'll see what is its intercept on x-axis. So when I drop a perpendicular from this vector to x-axis, it is cutting it at distance a. So for x-axis, the intercept made by this vector OA is a. Okay, and the intercept at y-axis. Now if I draw a perpendicular from this to y-axis, I'll see that this is minus y, because it's not plus y, because if it would be here, then it would be plus y, but because it's on another side and my origin is here, see what I'm saying is, this is my plus y, this is the origin, and I'm right now my OA vector is here. So when I drop the perpendicular, it will be at along minus y-axis, and this length is b, so this length will be minus b. The intercept will be at minus b, and this intercept is at positive axis, so I called it a. If it would be here, then its intercept will be at plus b. Right now its intercept is at minus b. Okay, so this will be minus b. And for z-axis, again you see this OA vector is only lying in this xy plane, so its intercept, I mean where it's cutting the z-axis, is at 0. It's just cutting the z-axis at 0, it's not anywhere else. So 0 times c. Now next step was, first step was to ensure that the vector starts from origin. Then second step is to write the intercept along x-axis, y-axis and z-axis. Then third step is to remove these ABC And what is the magnitude? We just write that. Here it's 1, here it's -1, here it's 0. Fourth step is to make it into integer, but here they are already in integer form, so there is no fourth step. And so at the last we have to write these these three numbers and put them in a square bracket. Now another way, whenever we have some negative integer, for Miller index we write it like this. We put this -1 at the top and we call it 1 bar. So instead of 1 minus 1 0, we write it 1 1 bar 0. Okay, the same thing. Either we can write like this or we can write like this. Usually it's denoted in this form. Okay, so the answer will be 1 1 bar 0. So B is the correct answer. I hope you understood. So right now, because it's passing through origin, so things are very easy, but sometimes they are very difficult questions. So that's why I'll try to do these as many as possible. Okay, so the next question. Here, the question is determine the index for the direction PA. Now you see the vector PA, for which we have to find out the Miller index in this cubic unit cell, which has edge length A, means all are A. Okay, its cubic unit cell means A, B, C is equal. Okay, and we can just call A. So here we see what was our first step to find out the Miller index for direction. It was to ensure that the direction is starting from the origin. Now here, if you see, it's not starting from the origin. Okay, it is lying on this plane, ending at this corner A, starting from this edge P, and the origin is somewhere else. So right now it is in this is actually YZ plane. Our vector is in YZ plane. That is not the problem. The only inconvenience is that it's not starting from origin. So we need to do something now to make it start from origin. And as I told few minutes back, that a vector, we can move it right, left, up, down, anything. It's just it should remain parallel. Everything is fine until we just move it parallel. So here also what we'll do is we'll move it parallel. Actually, I can tell you just by shifting the origin from this to this, like something like this. I'll show you. We have to either shift the unit cell or this vector such that right now it's starting from this edge P and going to this point A. Our origin is somewhere here, right? Our origin, okay. Our origin, it's difficult to write here. But anyway, this is our origin and we want it to start from origin. So one thing is we can shift something like this. And then you know what will happen? If I shift so that the starting is from origin, this is the end what? This was A, I think, this was P. Now P is at the same point as the origin. What is this? Okay, anyway. So now we have corrected this first step. But the problem is it will get difficult for you to visualize where the intercept is happening. Okay, so instead of shifting it like this, what we'll do is instead of shifting it like this, another thing that we can do is we'll shift this. Right now it is in the front plane, right? Right now it is in this front plane. We'll shift it because we can shift it parallelly anywhere. So we'll shift it in from the front plane to the back plane. When I'll do that, from this front plane, I'll shift it to back plane. So this was my A, this was my P, and this was origin. Now I have shifted from this A to A prime and this end from P to P prime. I hope you understood that the first step in writing the Miller index was to ensure that my vector is starting from origin. But if I do it like this, it will get confusing for you. Although I can tell you here also if I try, but I think it will get very confusing. There will be y-axis will be here. Okay, this will be z-axis, and then x-axis will be here, and then you have to find out the xyz intercept. But to keep it simple, because same technique we'll have to apply many other questions as well. So instead of doing that, let's just do the shifting, which is still easy to understand. So from here, I have earlier it was in the front plane, now I have shifted it to the back plane. Now here what happens, it still is not fulfilling our first criteria, because what I told you, first criteria was that vector should start from origin. Here it's not starting from origin, it's ending at the origin. Okay, in other two questions, when you saw, the vectors were beginning from origin and ending somewhere else. Here also it was beginning from origin, ending somewhere else. Then it becomes convenient to do this, write this Miller index. But here, even when I'm shifting, it's not starting from origin, it's ending at origin. So another way what we can do is, actually we can find out with this also. I'll tell you two methods here. One is based on some vector calculation, and another is just the usual intercept that we do with some little twist. Okay, so what, after the shifting, at least one of the two ends of this vector is on the origin, so half of our life has become easier. But still something will be different here. So now if I see the intercept of this end, okay, so it's, do you think it's making intercept at x-axis? No, because it's at the origin, and this is, because right now it's lying in the, this is y-axis, right, and this is z-axis, and this is x-axis. So right now the vector is lying in yz plane. Earlier also it was in yz plane, but that time it was at the front, now it is here. So x-intercept, you can see x-intercept is 0. What about y-intercept? If I drop a perpendicular, I see it's cutting at half distance, so a by 2. Okay, now where it's cutting the z-axis, if you draw a perpendicular here, you'll see it's cutting at distance a, because this all was a. So this x-intercept is 0, y-intercept is half, z-intercept is a. So this is done. Next step is to remove this a, b, c. Just keep the this integer, which is 0, half, 1. After this comes the step where we need to multiply these numbers such that we get integer. If I multiply all these three numbers by 2, then I will get 0, 1 and 2. Okay, so what I wanted to tell you here is, I told you, right, we can still proceed same way, but there will be a twist here, because here my vector is not starting from origin, but it's ending at origin. So the twist is that these numbers now will become negative. Okay, 0 anyway, positive, negative, it doesn't make sense. So this is the twist. I'll tell you in another vector form also, and you will see that this thing is correct. So whatever intercept we understood, that is fine, but because it's it's ending at origin and not starting from origin, so we have to take negative of these intercepts. Why I'm taking, I don't know if you can visualize, but if I extend this further, if you can visualize, I'm extending this further, and then the intercept will be in the minus y half. Okay, if you extend this minus y, and this is minus z. If I extend this here so that I fulfill the criteria that my vector is starting from origin, then if you take intercept on y, you see this is minus a by 2, and intercept on z axis, equal distance from there to here, it will be minus a, because the same unit cell, I mean it's little small here, but the same unit cell will be here. I don't know if you could understand or not, but that was the intention. Why, even though I'm keeping it here, why I have taken negative. If your visualization is good, then you can take it here, and then it's like where I moved, I'll tell you. It's like moving from, yeah, so it's like moving from this, no, this is also not good. Yeah, it's like moving from this unit cell to, this is not a good diagram. I think I have some diagram here. What I mean to say, it's like moving from this unit cell to this unit cell. Okay, so like if you keep it like this, then you have to take care of the negative sign. If you move this to this quadrant, not quadrant, octant, because it's divided in 8 spaces, so octant we call. So if it's like moving from this to this highlighted one, but if it's getting difficult to visualize, that's why I didn't want to go into that. So what you can simply do is just move it parallelly like this, so that at least one end of this vector is on the origin, and then just take care of the negative sign. Or then another short way, if you are confused about taking care of this sign, another way would be to do some vector calculation. So when you shift it like this from the front plane to the back plane, okay, I don't know, I have some diagram or not. It will be muted. So right now it was here, right? Let me explain this. So with vector, that I'm telling you, with vector calculation, how we can find out. Right now it was here initially in the question, and I'm shifting it to A. I'm shifting to A prime, which is also the origin, and P I'm shifting to P prime. Okay, this is my vector. Now you can see, if I call this as, this is z axis, we know, this is y axis, we know, and this was x axis. Okay, plus x plus y plus z axis. If I call this corner, array, what is this? If I call this corner as M prime, and this is origin anyway, also A prime, this is P prime. Okay, now what happens? You see P prime A prime is parallel to PA vector, of course, that's why we could shift it. Now if you consider now here P prime A prime, the vector direction is this, we can write it from triangle law of vector. If my vector is like this and this, then final one will be like this, right? So from that, P prime A prime will be the sum of P prime M prime and M prime A prime. So P prime A prime will be vector sum of this. Okay. Yeah. So P prime A prime is P prime M prime plus M prime A prime. This is through this vector calculation you can find out the intercepts easily. I am telling you both ways, whichever you find proper. I mean, I think even if it's still getting confused, I think when I'll upload this video, you go through slowly through all these steps to understand what's happening and what we are doing. If still you have doubt, you can of course ask next time, but just try to understand. So P prime A prime vector, I can write as vector sum of P prime M prime and M prime A prime vectors. Okay. Now what happens here is, now this P prime A prime, what is the length? What is the length of P prime A prime? We knew this was half, so this means this is also half, right? And this is along the y-axis, because this is y-axis means this is also y-axis. So this is, and now this is negative direction. If I'll go this direction, it's plus y, but I'm going this direction, it's minus y. So the intercept made by this is minus a by 2. And intercept made by M prime A prime. This is M prime, this is A prime. The distance of this vector is, again the direction is opposite to plus z. So minus, and the distance is A. Okay. And there is no x-axis intercept anyway. So the intercept for x-axis will be 0, intercept for y-axis will be minus half, intercept for z-axis will be minus 1. And multiplying with 2, it will be 0, minus 1, minus 2. So the direction will be 0, minus 1, minus 2. Or how do we write it? 0, 1 bar, 2 bar. So I just told you, either if you can take intercept and then just do minus here, or you can break into this vector sum and then take their length, take care of the direction and everything, and then also you can get. This was another way. Oh, sorry. Okay, moving on to another question. I don't know how much time we have. I have a lot of questions here. Or maybe I can now go to one question for plane. This is direction question. I think already we have done a lot, because yeah. Let's move on to some question for plane. Yeah. Okay. If we have time, sometime we can do it again. So here we have to find out the Miller index for the plane OPQR. So how to find? Like for directions, our first step was to ensure that our vector starts from origin. For Miller index, it's opposite. That we have to ensure that our plane should not intersect the origin. Otherwise, it's get difficult to understand that how to, where it's cutting the axis. Like here, if you see, like here, if you see, our plane OPQR is this. It's cutting the origin, so it gets difficult to tell where is it cutting, the z-axis or y-axis or x-axis. Okay. So when it comes to writing Miller index for plane, we have to ensure that our plane should not intersect origin. So how to do? Either you can shift the plane, or you can shift the unit cell. Somehow the origin we can shift. Because how we can shift it so conveniently? Because we said, right, any atom you take, on this whole crystal, all atoms have same neighborhood. So it doesn't matter. You can start your origin from here or here, anywhere, because the environment is identically same from any point. That's why we say it's a regular pattern, and that's why I told things become easy. So here, instead of taking origin here, we should shift our origin to this point, O prime. When I do this, now it becomes very clear. So where to find out that where is the plane cutting the x-axis and the y-axis and the z-axis. So first we need to find out the intercept. The plane, you can see this is the x-axis, right, parallel to this. This is plus axis, positive x-axis. The plane is not cutting the x-axis. This is my origin. You have to see the plane is just parallel to x-axis. It's not cutting anywhere. That means it's cutting it at infinity. Of course, you can write it A, but anyway, we have to drop this A later. And then the intercept, this plane is cutting the y-axis at where? The plane is cutting the y-axis at A minus 1 actually. Because if we take origin here, that means this becomes my minus y direction. So this is minus A and this is plus y. If this is origin, this is plus x, this will be minus x, opposite direction. This will be plus y, this will be minus y. So right now it's cutting it at minus A. And z-axis where it is cutting, this is plus z. It's cutting at half of this c by 2. Okay. Now next step is to drop, this is minus b. Next step is to drop these a, b, c and just write the magnitude, which is infinity, minus 1 and half. Okay. And now keep in mind, because this step was not there when we wanted to find out the Miller index for directions. So please be mindful. The next step here is to take reciprocal. This we do when we want to find out Miller index for planes only. You have to take reciprocal. Now this is cutting like 1 over infinity. This is 1 over minus 1. This is 1 divided by half means 2. What is 1 over infinity? 0. This will be minus 1. This will be 2. So now all I have to do is, and plane, for plane we denote using these curly brackets. So the correct answer will be 0, 1 bar 2. A is the correct answer. So please be mindful, shift origin, because our plane should not cross through the origin, otherwise it gets difficult to find out the intercept. After shifting the origin, find out the intercept for x-axis, y-axis, z-axis, then just omit these a, b, c and just write the magnitudes, take its reciprocal and put it in bracket. That will be your Miller index for that plane. Let's do one more question. We have to find out the Miller index for this plane GAE or AEG. Anything you can call, AEG, AGE, anything you can call. Okay, for this plane which looks like this here, first thing is to check if it's passing through the origin. We can very clearly see it's not passing through origin. That's a good thing. Next step is to find out its intercept for x-axis, y-axis, z-axis. Intercept. Okay. Intercept at x-axis is a plus a, because at front it's plus axis plus x-axis, right? So it's plus a. Intercept at y-axis is, because it's orthorhombic, means all sides are equal. So this is also plus a. And along z-axis it's cutting here, that is also plus a. Next step is to drop these a and only write the magnitude, which is 1, 1, 1. After that the step comes when we have to take reciprocal. Reciprocal of 1 is 1, and then we have to put them in parentheses. So the answer that is the Miller index for this plane is 111. Okay, so I have more questions, but I think because it's already time, if maybe I can do few of these questions next time also, because again, see here also what you have to do is, here what you see, we have a plane OAIH, OAIH. First step is to see if it's passing through origin. Here, unfortunately, it's passing through origin. Now what I'll do, I'll shift my origin. I'll see after shifting where I can easily find out. Like if I'll shift here, it will be difficult for me to find out the y intercept. So instead I'll shift here, or y or z intercept. So because I told all corner atoms are identical, so I'll shift my origin here. Now when I shift my origin here, this becomes y-axis, this becomes this becomes x-axis, and the top anyway was z-axis. Now when I do this, I see it's cutting x where this is origin. So down means, anyway, for x we see x, it's parallel to my x. That means x, it's cutting at infinity. Right? Y, where is it cutting? It is cutting y at half, or b by 2. Okay. It's cutting z where this is my origin, and it's cutting it at negative z, because this upper is plus z, below origin this all is minus z. It's cutting at minus c. Next step is to take only magnitude. Right, this was a, it doesn't matter. Only magnitude when I take, I will get this. Next step is to take reciprocal, 1 over infinity. This will be plus 2, this will be minus 1. This means 0. So 0 to 1 bar. This will be the correct answer. Okay. So this is same way you have to do. I think after these you will be able to solve. If it will be relevant, I'll do the remaining question next time also. But here we are already time up. So I think, and anyway, we discussed good questions where all this shifting of origin was involved. So main thing we have covered. Still, if required, we can discuss it next session. But now, if there is no more question, I'd like to stop the session. And yeah, if there is no doubt, then I'll stop the recording.